Hello, everyone. My name is Manish, and I'm the president of OneQuantum Nepal. I also work as a quantum engineer at IQM Quantum Computers. And today we'll tell you about the project we completed at OneQuantum Nepal. The project is about running Grover circuit on a real quantum computer. So what we did at OneQuantum Nepal is that we studied the theory of four-state Grover circuit, and our students, they have executed this circuit on a real quantum computer at IBM. Right. So first, I'll tell you briefly about OneQuantum Nepal. So at OneQuantum Nepal, we bring students, entrepreneurs, academics, government representatives, etc., from around the country together to catalyze a quantum ecosystem in Nepal. Right. So we started this initiative several months ago as a part of bigger OneQuantum, which is a not-for-profit initiative. Today, we have more than 200 people subscribed to our newsletter at OneQuantum Nepal. We hold weekly meetups virtually each week and invite exciting speakers in the field of quantum. These weekly meetups are very well attended, and we have received a lot of positive feedback, right, for it. And I want to show you our network as OneQuantum global community. And let me share my screen here. So we are growing as OneQuantum, and these are all the chapters we have managed to bring together. Our network extends from Chile in the west to Japan in the east, right? OneQuantum Nepal is here somewhere in between China and India. We have chapter that was recently introduced, OneQuantum India, OneQuantum Libya. We have a lot of chapters in Africa, right? And we have other dedicated chapters, right? As you can see here, dedicated chapter for women. We call it Women in Quantum. Another dedicated chapter for startups, right? So it's a very really an umbrella, right, where we bring together people from all walks of life within this initiative, right? A nonprofit initiative, and the main goal is to really catalyze, right, this ecosystem all over the world, and we offer really interesting features, right, from OneQuantum. For example, we have local content and resources, as you can see on this bullet points on the right. For global quantum community, we offer mentoring sessions, right? We have a free professionally run mentoring program. We match mentors with mentees through this platform that was offered by our partner Keysight Technologies, and we have over 400 mentees signed up for that, and about 100 mentors, and these mentors are experts in quantum and quantum computing in particular, and mentees, they get professional sort of tutor and like sort of knowledge transfer we attempt to do there, and for companies and of course for our members, right? At OneQuantum, we offer career fairs, resume DB for our employer partners, job board, so that they can attract talents for quantum workforce, right? And what is most interesting, one of the most interesting aspect of OneQuantum is we also offer realistic quantum computing projects, right? And these projects could be theoretical projects where people or members from OneQuantum, they sit down with their chapter presidents and work on an interesting problem using pen and paper. Or more interestingly, we encourage simulating quantum circuits on simulators and realistic quantum hardware, right? And within this domain of projects at OneQuantum Nepal, we have recently finished writing a code to run a Grover circuit on a simulator as well as on a real quantum computer. And this is one of our first projects, right, within the whole OneQuantum. and we have successfully managed to write a code for 4-state Grover's algorithm, which is a very prototypical quantum computing algorithm. And our OneQuantum Nepal enthusiasts, Abhiskar and Manish, they were heavily engaged in this project, and they mentored other OneQuantum Nepal members during our weekly meetups to accomplish this task. And now I will hand over to Abhiskar to describe Grover's circuit and what kind of results, right, he obtained or insights he had, looking into this Grover's algorithm, right? So Abhiskar, why don't you introduce yourself and maybe tell a few words about Grover's algorithm?
Okay, sir. Thank you, President Monish. It's me, Aviskar, and I'm quantum enthusiast from Nepal. Recently, I graduated from high school, and I'm working on OneQuantum Nepal currently, or I'm learning and exploring new things. Okay, I'll move towards our project, Grover's, to calculate our problem, and that was solved by Grover's algorithm. Let me share my screen. Okay. Yeah, here we go. The Grover's algorithm. Actually, the Grover's algorithm is an algorithm that sources the unstructured data from a database. Like it means if there are so many data that are unstructured, and if you want to find a particular data, or if you want to pick the particular data from that huge unstructured data, then Grover's algorithm is option to pick that particular data. Okay, here we go. At first, in OneQuantum Nepal, we took 2 qubits and 4 states. That has the 4 states. So we are doing this project in 2 qubits. We are testing in 2 qubits recently, and hopefully in future we can generalize into like n number of like states. Okay. The problem that actually the problem is that let us suppose there are 4 pages, and there are phone numbers of different peoples. So you have to pick a phone number of particular your friend or anyone that you like. So let's suppose that there are 4 pages, and let's suppose that X and 1 2 3 4, that's an array, and let's suppose that the required number that we want to pick is in page 2. So after that, how to get that data? So how quantum approach is better than classical approach? So in classical approach, like if the data is in second page, then you have to run some loop from first data and first page. So in average, if you try to run or try to find the solution of this problem through quantum approach, through classical approach, then you have to, in average, like you have to solve or you have to iterate that function for n by 2 times. But why we like n by 2 times, and it's a lot of iteration. It means you have to, like if there are 80 states, then you have 80 states, and if the phone number is in 8th page, then you have to flip the page 8 times. So but how we can reduce that time? So here we get the quantum approach and quantum computing. Okay, in the quantum approach, like Grover's speed of this source process, like through different advantage of quantum computing, from interference to like amplitude amplification mainly. So it will, in average, it will calculate it will find that particular data from that huge unstructured database in root n, in average of root n, or quadratically it will speed up the source process and data. So that's why it will find the data that we want very fast than classical computers does. Okay, there are many, there are different chunks that I want to express so that it will be easier to understand what exactly is there is a process to find that data. For that, I want to go to the graphical structure so I can easily explain what exactly the process is. At first, you can see that there are two qubits, QO and Q1. After that, there we applied the Hadamard gate. Actually the Hadamard gate is used to superpose the different states, and after that we applied the oracle function. Actually, the oracle function is applied so that we can perform that this project. There are different three chunks. That at first we applied Hadamard gate, and then after oracle, and then after diffuser. In diffuser, there we do the phase flips and uh, different Pauli gates Pauli G you can see in the structure, and through different states, and we can and I want to keep note that the diffuser function, the function that we made is only for 2 qubits right now, but if we want to generalize it, then we can generalize in future projects. So there are three process, like superposing, after that oracle, applying the oracle function, and after that applying the diffuser, so that we will get our desired output. And yeah, now I want to invite Manish Singh for quantum simulation and to run that code that we did in a real quantum hardware.
Okay, thank you, Aviska. Hello, everyone. I'm Manish Singh. I'm also a high school graduate from Nepal. I'm also one of the enthusiastic member of OneQuantum Nepal, and learning about quantum computing and searching its application wherever it applies in the context of Nepal. And moving to our presentation, let me share my screen. Okay. Okay, so now we go on applying our running our circuit on real quantum hardware. So we jump to Strangeworks platform. This Strangeworks platform allows us to access IBM hardware, so we can directly run our circuit on IBM hardware. So so we go with loading all our dependencies like NumPy and libraries. All we load all of them all at once, and then we define a variable named provider, which allows us to access to our IBM hardware. So here a Strangeworks provider allows us to access to IBM hardware, and then we go to our main function that we defined. And at first we define phase oracle gate, and we define in this gate takes two inputs as arguments. First, n, which is the number of page from which we want to search a particular page, and that particular page is named as a page to be located argument. So if we want to find any page, we will just put its name in the as second argument. And inside this phase oracle gate, at first we construct a quantum circuit consisting of n n circuit. n qubits, sorry, n qubits, and after that it constructs an identity matrix of n by n dimension, and after that we define this we change modify our matrix in such a way that it will flip the state that we want to locate, and leaving all other state unchanged, just acting as the identity gate to for other states. So basically the major takeaway from this circuit is that we define a operator such that it will only flip the state that we want to find from our whole diary. So if you want to find 0 1 state, then it will only flip 0 1 state, leaving all other states unmodified, and just acting as a identity gate for it. And after that we define diffuser operator. Under this diffuser, what this diffuser operator does is it just implements amplitude amplification such that the state that we had flipped earlier in phase oracle gate, that state will be the amplitude of that state will be amplified by certain extent, so that our probability of measuring such a state will be much higher. So this diffuser operator consists of first applying Hadamard gate, and then appending then applying oracle function just as we defined here, and again applying Hadamard gate. And after that we bring all these oracle operator and diffuser operator under single Grover circuit, which takes argument as the number of page we want to number of page from which we want to locate a particular page, and the and second argument as the particular page to which we want to locate find from our diary. And under this function, what it does is it first constructs quantum circuit consisting of uh, n qubits and classical register that also of n classical register also of n number of classical bits. And before inputting our state, what we do is we apply Hadamard gate such that we obtain a superposition state of all of our states, such that the equal probability of measuring each state is maintained. So if we have 4 state, this applying Hadamard gate maintains the equal probability of each state, 25% probability of each state. And after that we apply our phase oracle operator, and after that we add diffuser operator, and finally we measure it. So in our case we had in our problem we had uh, a diary consisting of 4 pages, so we'll uh, input n as 2 such that it will generate 4 states: 0 0 0 1 1 0 and 1 1, just as like this. And we label each state with certain page number such that the page 0 corresponds to 0 0 state, and similarly for other states as well, that we can see here. And after that we specify our backend, and yeah, at first we want to show running our circuit on a simulator and see what our result is. Before that, we specify input arguments as a circuit QC, just that we defined earlier, QC circuit, and number of shots. We are taking a large number of shots such that we obtain higher uh, precision in our measurement, and there are other arguments as well, which I don't think is much important for our problem here. And here we assign job to the provider, and after we collect the result from uh, the job assigned, and 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 finally we run our circuit on this simulator, and let's see what's our result. It will take a while. Okay, here, now it's done. Okay, so here is our result, and a number of shots performed 1024, and we count what's our result. So we are searching for 01 state, and all our sorts has given uh, 01 state. So that means 100% probability of measuring state 01. Uh, since we ran this circuit on a simulator, so it gave us 100% probability. Now we'll go back and run this circuit on actual hardware. We remove the hash, and here we go. Now our circuit is running on actual hardware. uh, IBM now Ruby is an actual hardware of IBM on which we have ran our circuit. It will display the result. Okay, here we performed 1024 searches, and here is the result. uh, and we obtained 00 state 49 times, and 01 state 959 times. So we can see the difference between simulator and actual hardware. So the actual hardware had some error, which is obvious because quantum computer is not so sufficient yet of now, and it goes like this. And we have successfully completed our circuit on uh, uh, real quantum hardware, and that's a result of our work. And by saying this, I want to conclude my presentation here. Thank you.
Thank you, Manis and Abhiskar. Well done. So I should point out this was really a joint effort by OneQuantum Nepal members that was, and this project was led by Abhiskar and Manis, and they did a fantastic job. And one must understand it's not so easy to play with new technologies in country like Nepal. As you can see, we have problems with electricity, internet, but they have managed to successfully run this project on real quantum computer, which is a really interesting feat, right, for OneQuantum Nepal. And I would like to thank you two again, and well done. You guys did a great job. And of course, we thank our partner at StrangeWorks, whose platform have been really, a very good educational tool for these guys and many others to learn quantum computing from. And it's a very useful platform for us to learn quantum computing. I'm going to continue to use this platform from StrangeWorks, and we are already looking into starting another project, and this time it will be about quantum optimization. And Abhiskar and Manish, they had some ideas about looking for a problem, maybe a combinatorial optimization problem that involves route optimization, right? For example, we can think of scenarios where we have cities in Nepal, there are hospitals in these cities, and we want to sort of find the optimal route, right? Because Nepal is a mountainous country, and we will benefit from a global optimum solution in this route finding problem, for instance. So our next project, which we'll do using StrangeWorks, will be a quantum optimization problem using suitably chosen quantum algorithm. And yes, we want to do that again together at OneQuantum Nepal in the next months. So yes, with that, we would like to conclude this small project demo from OneQuantum Nepal. And thank you to Abhiskar and Manish for nice presentation.